Okay, thanks for the great introduction. Also, thanks again for the invite me to nice workshop. Uh, Now I'll talk about the seamless integration of side channel preprocessing in deep neural networks, which is the work for the deep learning based side channels. Before talking about the mainstream, I briefly introduced the side channels. The cryptography algorithm is widely used for our life to protect the private data. For example, the cryptography algorithm is already used in the laptop and desktop and smartphone and so on. However, as we know, the device should be required to operate the cryptography algorithm. Uh, Unintentionally, some information comes up from the device. For example, power is naturally consumed to operate the cryptographic algorithm. Moreover, the electromagnetic emission is appeared as well. We call this information as the side channel information. Furthermore, this information is sometimes related to the secret key because the secret key is used while encryption algorithm is operated. In the worst case, depending on the secret key value, the power consumption might be changed. There might be different. We say this kind of the attack is called as side channel shift. The big category of the side challenges is divided into two concepts. One is non-profiled attack, and the other one is a profiled attack. In non-profiled attack, the adversary estimates the side channel leakage model for the target by commonly used method. Normally, Hamming weight and Hamming distance models are commonly employed. For example, in Hamming weight leakage model, we believe that the side channel leakage depends on the number of bit 1 in the data. This assumption is usually used to the software implementation. The other one is different from the Hamming weight model, which is used for the estimation of the hardware implementation leakage model. In terms of the profiling attack, the adversary wants to make the leakage model from the device to estimate the more accurate leakage model as compared to the non-profiling attack. To do this, we need to another device which is the same to target device. From the identical device, the adversary learns everything with public data and secret data. Based on the confirmed leakage model from the identical device, we can apply this model to the target device to find the correct key. Recently, the profiled side analysis is combined with deep learning. As I mentioned before, we can divide this attack to two steps. First, we collect the trace for the various input value with known key in device, which is identical to the target device. Then for training the deep learning, we put the trace as the input of the deep learning architecture. Since we already know the answer after comparing between the secret key value and the output of the deep learning, we can train the deep learning. Afterward, for attack, we collect the trace from the target device, then we give the trace to the trained deep learning architecture. If the model is well trained, the output provides the secret key. We call this attack as the deep learning side analysis. So I shortly introduce the motivation for this work. The main proposal is a framework to integration between the pre-processing and deep learning side analysis. Before our suggestion, many papers related to the deep learning side analysis focus on the direction of the design an efficient network, which is able to provide the best attacks against each side channel data set. On the other hand, the advantage of the pre-processing the training set was shown in few papers. To the best our knowledge, no work has investigated the possibility of the improving DNN architecture with the capability of the integration existing side channel pre-processing or filtering techniques. Moreover, there is no general framework up to the date that would help users with the overall trace analysis assisted by machine learning. Therefore, By integrating the classical preprocessing in site analysis area, we induce the minimizing the need for the architecture adjustments. In order to realize our motivation, we need to employ the preprocessing to the underlying deep learning architecture. To do this, we hired the multi-scale convolution neural network. Let me introduce this concept from the next slide. This concept was already proposed for the time series classifications. Since the side channel information is one of the time series, we can naturally apply this concept to the side channel series. Actually, the idea is very simple. The idea is to incorporate the picture extraction and classification in a single framework by using a multi-branch model. The architecture is divided into 3 parts. First part is a transformation state, which is actually input. We can imagine that the processing concept can be applied to the transformation stage. Actually, in original proposed paper, the identity mapping and downsampling and FFT transformation are used for 3 transformations. Next, in the mid part, conversion layers are applied to the each transformation data, which is induced to extract each pictures from the transformations. In last part, after concatenating the output of the local conversion stage, the classical CNN architecture is used, including the fully connected layers. As construction of the MCNN, we can get some advantages. Actually, as I mentioned before, the main advantage can be to extract the features from the various transformation. Therefore, as side channel leakage comes from the various operation working at different frequencies, MCNN is naturally suited for this problem. For more understanding our work, I briefly introduced some techniques and data set in terms of the profiling side analysis. The open tray dataset are used to measure the efficiency of profile site analysis, which is similar to the concept of the MNIST dataset in terms of the deep learning area. There are 4 public datasets. First, the ASCA dataset is for the false or the masked AES software implementation, especially the introduced the random jitter are set to range up to 50 and 100 sample point. These data are represented ASCA desync equal 50 and ASCA desync equal 100 respectively. And in ASRD, the trace have the no masking countermeasures of the implementation, but there is a random delay countermeasure to cause the misalignment in the traces. And the third and fourth dataset are hardware implementation. ASHD is no any countermeasure which is a pure hardware implementation for AES, but due to the FPGA, ASHD dataset has a lot of the noises. The last one in ASHDMM dataset, there is the multiplicate masked AES hardware implementation. Finally, we consider the various countermeasure and implementation to evaluate our architectures. So I introduced the 4 techniques to employ the classical preprocessing. First one is very easy to hire and usually used to break the jitter-based countermeasure, which is called as the moving average. The second one is commonly used to extract the picture by reducing the dimensions. This is PCA, which is used to combine with the profile size analysis in many papers. And the main goal of the third and fourth techniques is alignment. Third one is based on the DFT to align the trace, which is called as POC. The last one is based on the time warping algorithm to align. Especially the last one might induce to generate the artificial sample since the main focus of the elastic alignment is shape. This is a summation for the dataset and preprocessing techniques. And the last slide for the background is the how to evaluate the DLSCA. Actually, we hired the gassing entropy to evaluate the efficiency of the SCCA because some papers demonstrate the accuracy is not useful for the evaluation of the DLSCA. The gassing entropy is simple. After 100 times attack in randomly chosen trace from the test dataset, we calculate the average rank for the correct key. Gassing entropy equal 0 indicates the correct key is ranked the top, which means the correct key has been always recovered by the attacks. In the left figure, the red line attack is successful. The blue line attacks failed to recover the correct key, even though we used 5,000 traces. Next, I explained how to adjust the MCNN architecture for SCCA. As mentioned before, we can use the pre-processing techniques as branches. For this, we select the moving average and PCA as the basic pre-processing. For constructing the MCN architecture, we select the base network, is called as BN. We use the suggest CNS structure for the ASCAD DSync 100, which has 3 conversion and pooling layers. It can be split into 2 conversion and pooling layers for the local conversion stage, and the last one conversion and pooling layers for the pool conversion stage in MCNN. To make sure the model architecture is well fit for the SCA, we use 4 different candidate models. Candidate 1 is that one additional conversion layer was added to each branch, making the total number of the branch layers 3. And candidate 2 is same as candidate 1, but with removing the conversion layer after the branch merging. Candidate 3 is the same as candidate 2, but with adding an extra branch normalization step after the branch merging. Candidate 4 is one conversion layer is placed in the local conversion stage. 2 other conversion layers are in the pool conversion stage. When 5 different models are applied to the HD dataset, as you can see from the figure, the chosen MCNN architecture performs the best among the 5 models. In a different viewpoints, the 3 branch provides the best result as compared to the different number of branches. This is the final main structure for the MCNN. For the basic input, the identity function and moving average and the PCA are applied, and 2 conversion and pooling layers are adapted to the local conversion stage. The last one, conversion and pooling layers are employed to full conversion stage, including the fully connected layers. And this is a whole network architecture for the MCNN SCA. To investigate the effect of the preprocessing, we sometimes use the POC and EA techniques. And in order to fairly compare with the MCNN, we also use the preprocessing as the input of the base network. This is the notation for our work. We use 3 inputs for the MCN like this, and also we use the 1 input for the base network. Sometimes we use the plus notation, which is used as the input for the BN in order to fairly compare with the MCNN, indicates merging of the data set. And for the various MCNN and BN, I show the experiment result. For hardware implementation dataset, the transformation of the trace alone does not give the good results as shown for the BN moving average 100 and BN PCA in both figures. This shows that it is an inherent property of the MCNN which allows it to run more features than PN alone and result in better attacks. Actually, the PN is not designed for the ASH, and therefore the results are worse than the best result in other paper. Still, we show significant improvement with the MCNN. The ASRD and the original ASCA dataset are easy to break, as shown in various the previous works. We also show that both MCNN and PN have no trouble in running these dataset and perform very well. And the jitter-based countermeasure for the ASCA, PM performs the best result in the right figure of the figure 6 because PN is optimized for the ASCA 100, while MCNN performs so fine in this case, is not as good as PN. We can expect PN to perform well in it, but our results show that PN is not good with this dataset and MCNN performs best because ASCA 50 is a subset of the ASCA 100. As mentioned before, because PN is fine-tuned for the ASCA 100, it performs the best on the particular dataset, but its performance on other dataset is not guaranteed. And MCNN does not outperform the best result when considering the architecture optimized for each dataset, and is not the objective of this work. In other words, MCNN is proposed as a common architecture that would generalize better across the dataset. Unlike the previous experience, we perform the attack in different sites. First, we consider the different training set and test set to demonstrate the generalization of our scheme. In this case, the training dataset is derived from the ASCA 50, while the test dataset is derived from the ASCA 100. This means the test dataset in worse quality than the training. In left of the figure 7, it can be clearly seen that MCNN outperforms the base network. The opposite result is in right of the figures 7. The performance of the both network is similar. And also we investigate the effect of the preprocessing techniques. Surprisingly, when we use the POC as one of the 3 inputs of the MCNN is right better than the base network, even though the base network is optimized for the ASCA 100 dataset. Of course, any preprocessing techniques can be seamlessly integrated to our model. POC is used as an example here. Therefore, we can finally say that in general, for all the experiments conducted, we can observe that the performance of the MCNN is constant throughout different dataset and different parameter settings. And I'll talk about the conclusion and the further work. We propose a general framework that can be used for the building MCNN models that can efficiently perform SCA tasks on various datasets without fine-tuning of parameter. For further work, different branches could be explored to enhance the feature transformation step such as the autoencoders. Moreover, we only consider the non-profiling data preprocess techniques. Therefore, it would be interesting to investigate the profiling preprocessing such as the LDA. If you have any questions, feel free to contact me or the Telao. Yep.
Have a question actually from the audience. So they would like to ask, how do you calculate the guessing entropy and why do you choose this as a metric?
As I mentioned before, sorry. Right? Because the many papers that use the guessing entropy in terms of the site analysis area, how to calculate. For example, you attack one time, the quality is rank 1, for example, first attack, and second attack, the quality is rank the top 2. We average this 1 plus 2 divide 2, and the rank is 1.5, for example. We repeat 100 times to calculate the guessing entropy. That means the average rank for the correct key.
The second question that we have here is, did you check your framework on a difference like masking?
Different masking scheme, you mean?
Yeah,
For
like
example, the arithmetic masking or the other
masking.
Sorry?
Did you test MCNN on masking?
Which masking?
Any type of masking?
We only consider the Boolean masking to break the Boolean masking and the multiplicate masking. Because the ACE HDMM has the multiplicate masking, and the other dataset almost has the Boolean masking. You see the summarization paper.
Another question from the audience, Yoo-Seung, is like when you train traces data from a microcontroller that is with a Hamming weight model, or you train traces from an FPGA, which is a Hamming distance model, is the training process the same, or do you have to change the training process?
What is the meaning of the training process?
Like the process to train the neural network. Is it exactly the same for Hamming distance and Hamming weight model, or microcontroller and an FPGA, or do you have to change it?
It's different. Because the change is the leakage model.
So what is the difference between these two techniques?
The techniques mean the DLSCA, you mean?
No, I mean, what is like, how is training from a Hamming weight model, like what does a designer has to do to change from a Hamming weight to a Hamming distance model in terms of the neural network architecture?
If you want to use the Hamming weight and Hamming leakage model, you have to change the number of the output. The current architecture is the number of the output is 256, because we consider the byte.
Okay, so you were training on the identity model.
Yeah.
I have one more question actually. We see that MCNN is actually a concatenation of 3 different networks which are learning different kind of features from each branch, right?
Yeah.
So how about the timing penalty? So for example, if you pre-process it before and then feed it to a single network, like is it from a training time, is it better, or MCNN is able to accelerate it faster?
Yeah, actually the MCNN is almost 3 times slower than the base network, because the MCN has 3 branches. That means that the input size of the 3 times as compared to the original traces.
Another question from the audience: did you try different number of transformation. So
transformation. Yeah. I also. Yeah. This one? Oh no. Yeah, this one. We consider the POC, sometimes the POC and EA. The POC, EA means the elastic alignment, and POC means the pace only correlation. The dark red line is POC, and light gray is EA. Sometimes the other preprocessing is better than the current preprocessing. It depends on the data set.
all right.
Yeah.
Thanks, Yoo-Seung. I don't see any other questions from the audience. So thanks again for sharing this talk. It was quite interesting.
Thank you.
So with this, actually, we are halfway through the first day. So at this